We're group 6 and we're creating a portable fluorescent sensor for Lyme disease antibody detection. My name is Christian Pearson and I'm majoring in photonic sciences and optical engineering.
My name is Christian Spurgeon. I'm majoring in photonic science and optical engineering.
My name is Aaron Jevitt. I'm majoring in computer engineering.
And my name is Gene Morales and I'm majoring in electrical engineering.
This diagram represents our team's roles throughout our project's design and implementation. I designed optical testing plans and created the fluorescent solution concentrations for testing. Chris modeled and printed our device's enclosure and holders. Chris and I collaborated on designing optical filter curvatures, determining the optimal angle of emission and detection, along with determining the positioning of optical components. Aaron designed our device's software, including the calculation of antibody molar concentration. Gene implemented the display system and designed our device's signal amplification. Aaron and Gene collaborated on circuit design, PCB layout, and the photocurrent processing.
For the project's goals and objectives, we have to create a device which accurately and precisely excites fluorophores of particular interest that are attached to Lyme disease antibodies by selecting a fluorescent marker, determining the excitation and emission wavelength of the fluorescent marker, and to find an illumination source with a peak emission wavelength equal to the excitation wavelength of the fluorophore. To create a device which accurately and precisely measures the concentration of fluorescent emission from the fluorophores, the photodetector chosen has a high sensitivity with the fluorescence emission in the wavelength range. The optical filters chosen are to isolate the fluorescent emission wavelength and to cut off the excitation light. It's compact design with reduced weight and bulk compared to other fluorescent sensing devices through the use of angled illumination, reflection, and detection. And the circuit is compact. The design is portable for the use outside of the lab. It has a long battery life and it has a rechargeable battery. As a visual display of sample concentration of fluorophores representing a particular element detected through fluorescence. The display has a high enough pixel count to display the decimal quantities with units of molar concentration.
The low cost and portability of our device allow for detection of Lyme disease antibodies outside of the lab. This will shorten the time between detection of Lyme disease and treatment of the patient. The compact size and use of curved optical filters in our device will be used to inspire customers to take advantage of Everix's thin optical filter technology. In order to test our device, molar concentrations of the fluorescent marker must be created. Next, the photocurrent output by the photodiode is tested. Then the limit of detection of our device is determined. Next, we must determine the voltage to molar concentration equation and implement it into our device software. Then we will compare our device's concentration reading with the true molar concentration.
We'll start by demoing the normal operation of the device. You can see a sample being inserted, the cover is installed, and the button is pressed to initiate a reading. Here you can see the LED flashing and the reading in progress. Once the reading is complete, you can see last sample was 13,687 nanomolar. This is very close to what we expect this sample to be. That's a very high concentration. Now we'll switch to a sample with a very low concentration. With this sample, we expect a very low molarity reading. Once the reading is complete, it'll average the samples together and we'll get 296.19 nanomolar. This is what we expect for this sample. The device is also capable of being accessed by a remote web UI. By connecting to the device's SD1 demo Wi-Fi network, we can then pull up a web page that will allow us to take readings and view the readings. Here we're just waiting for the Wi-Fi to connect. There we go. Now we click take reading, and after a moment, it's still initializing. Now we have a reading. You can see the time, the voltage, and the molarity rating. We're currently using the very high molarity sample for this demonstration. So every time I press take reading, the device is taking a reading and displaying both the raw voltage reading and the molarity. Next, we'll demo profile selection on the device. By pressing and holding, the user can enter profile selection mode. The profiles contain a conversion factor for voltage to molarity, the number of samples per reading, and the delay of activation that allows the LED to saturate the sample and create fluorescence. By clicking the button, you can toggle through the pre-made profiles, and pressing and holding returns us to the main menu. Here, if we press the button, we'll trigger a reading. You can see the LED is blinking and using the new profile delay instead of the original one we were on, user profile 1. This sample was taken with no vial in the device. That's why 0.0 nanomolar can be seen. On the screen now is the ESP32 running a generic web server that just shows the text, "Hi, I am ESP32. So we'll go to the page /update and choose a precompiled binary file of our senior design code. Once this progress bar completes and we go back to the main page, you'll see that instead of "Hi, I'm ESP32, it now shows our normal web GUI and is able to take readings. This is going to be very useful for our end design where we don't need USB or programmer access to the chip, and the end user could also flash custom firmware updates without that same access.